A very good evening, one and all. Am I clearly audible to you?
Sir, you are audible.
Thank you, ma'am. So, is my screen visible to you?
Yes, sir, it is visible.
Yeah, thank you. Thank you very much. So, I hope you had a great Sunday. So, the agenda for today is to cover ensemble methods. We have already seen some of the ensemble methods. In the today's session, we'll be looking at gradient boosting technique. And in the next session, Dr. Balaprakash will cover reinforcement learning. Reinforcement learning, some part of the reinforcement learning he will cover today and some part in tomorrow's session. Okay, so there was a small change in the schedule. Sanjay ma'am supposed to take second section according to the plan schedule, but there is a small change in the schedule. Right. So because of that, Balaprakash sir will take reinforcement learning in the second section. So that's the agenda for today. So in the current section, we're going to discuss gradient boosting technique, which is also one of the ensemble learning technique. Right. So in this, we're gonna see what is gradient boosting, brief history of gradient boosting and gradient boosting for regression, gradient boosting for classification, and a demo of gradient boosting. And also relationship between AdaBoost and the gradient boosting and why it works. All these things we're gonna cover in this session. Right. So just to recollect AdaBoost, we have seen AdaBoost technique yesterday, right? In the yesterday class, we have seen AdaBoost technique in which we are taking some weak learner and classifying the or predicting the training data. And we are increasing the weight for the data points wherever the model is making mistake and we increasing the data points where the model is correctly predicting. So as per the new weightage, we are learning another classifier and we are repeating the same procedure. Upweighting the incorrectly classified instances and downweighting the correctly classified instances. And as per the new weightage, again we are learning another classifier and we are upweighting the incorrectly classified instances and downweighting the correctly classified instances, and we are repeating this process for number of iterations. Right. So this is ADA boosting technique. What is gradient boosting? Gradient boosting is a gradient descent plus boosting technique. Right. So how this works, we'll see in the coming slides. Right. So in the case of boosting technique, what are we doing? We are fitting an additive model in a forward stage-wise manner. And in each stage, we are introducing a weak learner to compensate the shortcomings of the existing weak learners. That's what we are doing, right? We are identifying the shortcomings of the existing learners and we are representing with them with a high weighted data. So once we represent the shortcomings with the high weighted data, what are we doing? We are learning a new hypothesis which represents the shortcomings of the existing weak learners. Right. So in each stage, we are introducing a weak learner to compensate the shortcomings of existing weak learners. So in data boosting technique, the shortcomings are identified by high weighted data points. Okay, so the only difference between the gradient descent and the data boosting technique is how we identify the shortcomings. In the case of data boosting technique, we are identifying the shortcomings by using high weighted data points. And in the case of gradient boosting, we identify the shortcomings using gradients. Okay, let's see how would we do that. Okay, so this is data boosting technique, just to recollect, right? So this is the hypothesis. Forward stage-wise manner, we are fitting an additive model, and finally, we are taking the hypothesis as an aggregate of the individual models, right? So, yeah, I'm just remembering something. Prashant, are you there? Prashant is not there. Okay, all right. Yeah. So this is how we fit the additive model in a forward stage-wise manner, and you can see that multiple weak learners together combined together and giving a strong non-linear hypothesis. Right? So let's see now the gradient boosting technique. In this also, we fit an additive model in a forward stage-wise manner. The same thing here also we are doing in case of gradient boosting technique also. And each stage, we introduce the weak learner to compensate the shortcomings of existing weak learners. Right? So the same thing we are doing in case of ADA boosting technique. Right? In gradient boosting, shortcomings are identified by gradients, not by the high weighted data points. So remember, in the case of ADA boosting technique, shortcomings are identified by high weighted data points, whereas in case of gradient boosting, shortcomings are identified by gradients. That's the difference between the ADA boosting technique and the gradient boosting technique. And both high weighted data points and gradients tell us how to improve our model. So whatever you take, right, however you represent the shortcomings, this high weighted data or the gradient, they tell you how to improve your model. It tells you where the existing models fail, right? So now the question is, and why, why and how did researchers invent gradient boosting technique? Okay, so this is a brief history of this gradient boosting. So in 1996, Front invented the ADA boosting technique. It was the first successful boosting algorithm. And in 1998, they formulated ADA boosting as a gradient descent algorithm with a special loss function. So it is not generalized to all the loss functions. With a special loss function, they formulated ADA boosting technique as a gradient descent algorithm. And then in 2000, it is generalized to all the loss functions to handle all the loss functions. This is a brief history of the gradient boosting technique. Okay, and gradient boosting is exist for different kinds of problems, like regression, classification, and ranking. And the difficulty level, if you see, gradient boosting for regression is easy as compared to the classification, and gradient boosting for classification is easier than gradient boosting for ranking technique. So we're gonna cover gradient boosting for regression and gradient boosting for classification in this session. Right. So for now, let's play a game. Forget about gradient boosting and let's play a game. Okay. So you're given x1, y1, x2, y2, so on, xn, yn. This is the data set given to you, right? Where xi is the feature vector, yi is the corresponding class level. And the task is to fit a model f of x to minimize the squared loss, which is a typical regression problem, right? We want to minimize the difference between the actual and the predicted, and we take squared loss to minimize that, right? Suppose your friend want to help you and he gave you some model f. Let's say that is f. Your friend want to help you, he gave you some model. Let's say that is f. Okay, and you have checked his model and found that model is good but not perfect. You have checked his model, you found that the model is good but not perfect. It means what? There are some small mistakes. Like if the actual value is 0.9, your friend model is predicting it as 0.8. If the actual value is 1.3, your friend's model is predicting it as 1.4. So very minor mistakes. Okay, it's nearly perfect, but it is not perfect. So now, how can you improve this model? Is the question. Okay, so there are some rules of this game. What are the rules? Rules of the game is that you are not allowed to remove anything from f or change any parameter in the f. So you're not allowed to change any theta values in the function f or not allowed to remove anything from f. So these are the rules of the game. Okay, so anyone, how do you improve it? Anyone? Just guess what is there. Right. You have some function f of x which is good model, but not a perfect model, and you have to improve. But rule of the game is that you're not allowed to remove anything from F or change any parameter in F. So any guess? Any guess from any of the participants? No? Okay, let's see. So you can add an additional model h to f so that the new prediction will be f of x plus h of x. In this, you're not changing anything in f. You're just adding an additional model to to just predict the parts where the existing model is failing. Right? So it means what? You wish to improve your model such that f of x plus h of x is equivalent to y. F of xi plus h of xi is equivalent to yi. So f of xi plus h of xi is equivalent to yi. Isn't it? Is it possible? Agree? So are you changing anything in f in this case? You're not removing anything from f, or you're not changing any parameter of f, isn't it? Is the rule of the game satisfied or not? Yes. Good. Right. It is satisfied. Right? So equivalently, you can say that h of xi is equivalent to yi minus f of xi. We can write that, right? F of xi plus h of xi is equivalent to yi. So therefore, h of xi is yi minus f of xi. Right? So can any regression tree or any regression model H achieve this goal perfectly? Maybe not. Right? Maybe not. May not be achieved, right? You cannot fit a perfect model that fits to this H of xi. But some regression tree might be able to do this approximately, definitely. Right? So how? Because we just fitting a regression tree H to the data. So according to this, the updated data is xi comma yi minus f of xi, x2 comma y2 minus f of x2, and so on. Right? So we're not fitting a regression tree to the original data. So this is the updated data. What is the original data? X1, Y1, X2, Y2, so on, Xn, Yn. Okay, so your friend model is giving something f of x1, f of x2, so on. Right? So if you remove this f of xi part where your friend model is predicting, you will get yi minus f of xi. So these are the parts where the existing model couldn't do well. So you have to fit another model to address the shortcomings of the existing model. Right? So this is the part where the existing model is failing, where the existing model couldn't predict it perfectly. So to compensate the shortcomings of the existing model, you're trying to fit a regression model to this residual part where the existing model couldn't predict it correctly. Right? So instead of taking yi, now your target is yi minus f of xi. Your target is changing now. Earlier it is yi, now it is yi minus f of xi. Got it? Following me? Are you with me so far?
Yes, sir.
Yeah, right. Thank you. So, yeah, good. We have got a better model, right? So here we call this yi minus f of xi as the residual part. So these are the parts that the existing model f cannot do well. And the role of this new model h is to compensate the shortcomings of the existing model f, right? So, so now the question is, if the new model f plus h is still not satisfactory, what would you do? The new model f plus h is still not satisfactory. It has not reached to the satisfactory level. Right? So what would you do? More residuals? Somebody said more residuals. Any other answer? If the a plus h is still not satisfactory, then it means that there are some residual parts that are still not still need to be addressed, right? So you can add another model, let's say H dash, to compensate the shortcomings of both of these two models, isn't it? Yes, sir. Cinema said more residuals we have. So we try to fit in another model to address those residuals. Right. So we can add another model to compensate the shortcomings of these two models. So now the another question is, we are improving the predictions of training data. Is the procedure also useful for the test data? So definitely, because we are building a model and model can be applied to any data. So because you're building a model and the model can be applied to any test data, yes, it is applicable to the test data as well. Now the question is, $1 million question is, how this related to gradient descent? You're claiming that it is gradient descent plus boosting. How is this related to gradient descent? Is the procedure clear? What are we doing? What are we doing? We are taking the original data, we are trying to fit a regression model to it and taking the residual term as the target in the second iteration and trying to fit another regression model to it and taking the residual term again and trying to fit the regression tree to this data by taking the residual part as the target. Right? So that's what we are doing. Stage-wise manner, we are fitting these models. And every time we are trying to compensate the shortcomings of the existing models. And the shortcomings are identified using the residual terms. Okay, so is that clear so far? The procedure that what we are doing? I think it is Sunday effect. Responses are getting responses late. Okay, so I'm also feeling lazy. Dowsing. Right. So, yeah, so I hope that is clear. So let's proceed. Hangover. Yeah, Sunday hangover, Sheikh Rasul. So let's come out of that. So, yeah, now the question is, how is this related to gradient descent? How is this related to gradient descent? Right. So what is gradient descent? Let us have just review about it. In gradient descent, what are we doing? We are minimizing a function by moving in the opposite direction of the gradient, isn't it? Like if the slope or the gradient is positive, we are incrementing theta, sorry, decrement positive, then we are decrementing theta value. If it is negative, then we are incrementing theta value. Right? It means we are moving in the opposite direction of the gradient. So we are trying to minimize the function by moving in the opposite direction of the gradient. Right? So is it that what we are doing in that gradient descent algorithm? Right? Now the question is, how is this related to the gradient descent algorithm? How the residuals are equivalent to the gradient descent algorithm. Let us see that. So our loss function is this y minus f of x whole square by 2. Right? We want to minimize this loss function by taking sum over I equal to 1 to n loss of this individual instances. So we want to minimize this loss function by adjusting f of x1, f of x2, so on, f of xn. Right. So please note here that we are not adjusting theta values. We want to adjust f of x1, f of x2, so on, f of xn. If you take the linear regression, what are we adjusting? We are adjusting the parameters. We are adjusting the parameters of the model. Theta naught, theta 1, theta 2, so on, theta d. But here, we don't want to adjust the parameters. We want to adjust the function. We want to minimize loss by adjusting the function f of x1, f of x2, so on, f of xn. And also note that here f of x1, f of x2 or f of xn are just some predictions. It means they're just some numbers. So you can treat them as the parameters and take the derivative, isn't it? Because they're just some numbers, you can treat this f of xi as the parameters and you take the derivative of with respect to this. Right? So you just want to adjust, you just want to improve the model by adjusting f of xi. And f of xi is just like a number. So you treat this f of xi like a parameter and take the derivative of j with respect to that parameter. Right. So derivative of j with respect to f of xi, if you take, what would you get? Derivative of j with respect to f of xi. This 2 come this side, 2 and 2 will get cancelled. You will get y minus f of xi times minus 1. It means y minus f of xi times minus 1. So this would be equivalent to f of xi minus y. So when you take the derivative of j with respect to f of xi, you are getting f of xi minus y. So we can interpret the residuals as the negative gradients. So isn't it? So this is gradient. If you take the negative of the gradient minus of this, what would you get? yi minus f of xi. So isn't it the residual? Right. So that is equivalent to the residual. Right. So the negative gradient is equivalent to the gradient. Right. So f of xi is equivalent to f of xi plus h of xi. We want to update the existing model. We want to add another model that compensates the shortcomings of the existing model f of x. Right. So that is why we are fitting an additional model h of x. Right. Fitting an additional model h of x is equivalent to fitting a model to y minus f of x. And that is equivalent to negative gradient descent. So what are we doing? F of x equivalent to f of x minus 1 time derivative of j with respect to f of x. Isn't it looking in this form? Theta equal to theta minus alpha times derivative of j with respect to theta j. Right? So it is in the same form. Right? So residual is equivalent to negative gradient. Fitting h to the residual is equivalent to fitting h to the negative gradient, and updating f based on the residual is equivalent to updating f based on the negative gradient. That is why we are calling this as a gradient descent. It is gradient descent plus boosting. Right? Because we have proved that residual is equivalent to negative gradient, and fitting any model to the residual part is equivalent to fitting any model to the negative gradient. So therefore, updating this f based on the residual is equivalent to updating f based on the negative gradient. And also remember that this is regression with square laws. This all that we are doing is for square laws. So we are actually updating our model using gradient descent technique. So it turns out that the concept of residual is more generalized than the concept of this. Sorry, I'm telling you in reverse way. The concept of gradient is more general than the concept of the residuals. So let us stick to this gradient word from now onwards instead of using the residual word. Right. So the reason we'll understand it later in the coming slides. Okay, so let us summarize the algorithm we just derived using the concept of the gradients. So compute the negative gradient. Negative gradient minus z of xi is derivative of minus of derivative of the loss function with respect to f of xi, which is equivalent to y minus f of xi. Okay, so start with some initial model, some weak model. Let's say it is the average of the individual YI values. So simple model, right? So let's start with some initial model f of xi and iterate until converges. You repeat this in some loop. Calculate the negative gradients minus z of xi, which is this, which means the residual in this case, but not necessarily in all the loss functions. So calculate the negative gradient minus z of xi. Put a regression tree or regression model h to the negative gradient descent and add this model, update this model f equal to f plus h. Okay, and repeat this process. Alright, so that's what we are doing. So the benefit of formulating the algorithm using gradient is that it allows us to consider the other loss functions. and derive the corresponding algorithm in the same way. Okay, so the benefit of formulating this using gradient descent is that it allows us to consider the other loss functions. You need not restrict yourself to the square loss functions. Right? Right. So for every loss function, you can compute the negative gradient descent and calculate the negative gradient to and fit the regression tree model to the negative gradient and update the model. So this process can be repeated. Right. Now the question coming in is, why do we have to consider the other loss functions at all? Why do we have to consider the other loss functions at all? Isn't it the square loss good enough? Right. So this is the question that is coming in this particular situation. Right. So why do we need to consider the other loss functions? Isn't it the square loss good enough? So let us see what is the problem with the square loss. Right. So if you take the square loss, it is easy to deal with mathematically, but it is not robust to outliers. Like if you take the outlier, this is a point, outlier point, which is very different from the other points, that is 5. So the prediction is 1.7 for this, right? And all the other points are the normal points and the prediction is close to them. So if you see this, the corresponding loss corresponding to the individual points, if this is close, then the loss is very less. This is close, so the loss is also less. This is also not that close, but little close, the loss is less only. But if you see this, the actual value is 5 and the predicted value is 1.7. So there is a gap between the actual and the predicted because it is an outlier, right? So the loss is very high. Okay, so what is happening here? You're penalizing these outliers heavily. The outliers are punished heavily. So as a result, what would happen? You're paying too much attention to these outliers and trying hard to incorporate these outlier points into the model. So as a result, the overall performance would be degraded. Right? So what is the problem with punishing these outlier points heavily? You will be paying too much attention to the outliers, trying very hard to incorporate them into the model. So which internally degrades the overall performance of the model. Okay, so that is the problem with this square loss function. Okay, so whereas if you consider the other loss functions like absolute loss function, absolute difference between the actual and the predicted, or the Huber loss function, which take the square loss up to certain threshold, if it exceeds, it applies a different formula, right? Absolute loss with some threshold setup, right? Like this, right? So let us see them. So if you see square loss, the outlier is heavily punished here, whereas if you take the absolute loss, it is not punishing that much as compared to the square loss. And if you take Huber loss with delta as 0.5, you can see that it is giving very less punishment as compared to the absolute loss and square loss. Okay, so as a result, what would happen? Even if there is an outlier, you will not pay too much attention to it, and you will not try hard to incorporate that into the model. Instead, you will just ignore that outlier point. Right? So, so that is the advantage of the absolute loss or the Huber loss. They don't pay too much attention to the outliers. Right. So the procedure is same for the regression with absolute loss or regression with the Huber loss. Right. Uh, yes, Prashant. Delta is the hyperparameter. So start with initial model and calculate the negative gradient and fit the regression tree H to the negative gradient descent and update the model. So the algorithm is same. Only thing that is changing is this negative gradient descent. Earlier it is yi minus f of xi. Here now it is sine of yi minus f of xi. Okay. So this negative gradient is changing. So note here that negative gradient descent is not equivalent to the residual in general. Okay, but the concept of residual is more, the concept of residual is more general than the concept, sorry, concept of gradient is more general than the concept of the residual. Right. Similarly, you can compute the negative gradient for the Hubbard laws. So this is the negative gradient, and you can fit or compute the negative gradient descent like this, and fit a regression tree H to the negative gradient descent, and F equal, you can update the model like this, F equal to F plus rho H. Right. So the general procedure is, given any differentiable loss function, start with the initial model, iterate until convergence by computing negative gradient descent and fitting a regression tree H to the negative gradient descent and update the model F equal to F less H. Right. So in general, negative gradient is not equivalent to the residual, and we should follow the negative gradient descent, negative gradient rather than the residual. Why? Why? Because if you follow the residual part for each and every loss function, you will be paying too much attention to the outliers. Let's see how that happens. Like for example, if you consider the negative gradient versus residual in case of Hubbard loss, right? So this is the Hubbard loss. If you update based on the negative gradient, this is the result. And if you update based on the residual, this is the h of xi. Minus z of xi is this, and h of xi is y. If you consider residual is yi minus f of xi. So the difference here is negative gradient pays less attention to the outliers, because if you see this, if it is less than certain threshold, then only you are applying minus f of xi. If it is greater than certain threshold, then you are considering something different. Okay, but whereas in this case, for any case, it is only considering the residual parts. Right. So if you update based on the residual, it pays too much attention to the outliers. If you pay too much attention to the outliers, the you will mess up with the original model. Right. So it may lead to erroneous results. You try very hard to incorporate this outlier points into the model, which degrades the overall performance of the model. Right. Whereas if you consider the updation based on the negative gradient descent, you will not be paying too much attention to the outliers. Right. So summary of this regression model is, we are fitting an additive model F in a forward stage-wise manner. In each stage, we are introducing a new regression model to compensate the shortcomings of the existing model. And the shortcomings are identified using the negative gradients. And for any loss function, we can derive this gradient boosting algorithm. And absolute loss and Hubbard loss are more robust to outliers as compared to square loss. Right? So this is the summary of this gradient boosting for regression. If you have any query, I'll take. Otherwise, we'll move to the gradient boosting for classification. Any queries so far? Following it? Any problem? Following it? Okay. All right. So Prashant, so after the session, I've realized something yesterday. I mean, I got a doubt, not realization, I've got a doubt. So
Yes, sir.
when you were asking this yesterday about this ADA boosting technique,
Yes, sir.
so you said that it is only true for the binary classification.
Yeah.
Yeah, so what is happening? Okay. And I said that yes, this we are doing for binary classification in this case, and if you want to do it for the multi-class classification problem, you have to change this aggregation strategy. Okay.
Yes, sir.
So, I mean, you didn't understand that gradient boosting, sorry, ADA boosting is only for binary classification.
Okay.
I didn't convey that to you, right?
Yeah, I mean, I thought I should look into it properly, and maybe I didn't.
It can be for the multi-class classification problem also. So I got a doubt. Maybe you got that. I mean, it went to your mind that it is only for binary classification problem.
Maybe but with the example, I got that dot. Maybe I have to look into the
So this
algorithm.
is for both binary and multi-class. The only thing is that the aggregation strategy you have to change probably. So there it is taken sign of the weight over the individual predictions, right?
Yes.
Sign of. If you want to do it for the multi-class classification, you take the weighted
Weighted.
voting, and whichever class gets more number of votes, you can assign that class.
Okay. Okay.
Yeah, weighted
Weighted.
voting, not
Okay.
general voting, weighted voting.
Okay. That's also specified in the algorithm, sir.
That was not specified in the algorithm. That's why I told you have to change the aggregation strategy
Okay. Okay. Okay, sir.
if you want to do it for multi-class.
Yes, sir. Yes. So actually, in this session, actually, due to some network issues, I didn't. It was not audible for me, and
No
so I
problem.
just.
You can go through the video later on. If you have any
Yes.
queries, you can get back to
Yeah,
me.
yeah. Just one small doubt, sir. This gradient boosting is only for regression trees or regression or for classification also.
Classification also, it is there for ranking also. We're going to discuss regression and classification. Regression we have completed and classification now we are discussing. We're
Okay, sir.
starting there. Gradient boosting for classification if you see the
Okay.
slide.
Oh, yeah. Okay, sir. Okay,
Yeah,
sir.
yeah,
Thank you, sir.
yeah. All right. Right. So here we're going to discuss gradient boosting for classification. The problem that we're going to see is recognizing the handwritten capital letters. So it is a multi-class classification problem. Obviously, we have 26 classes A to Z, and the letter is looking something like this. This is an example instance Z. Okay, and this data set is from this archive, from this link, 20,000 data points and 16 features. And these are the 16 features. So given an image, you can extract the features like this. Horizontal position of the box, vertical position of the box, width of the box, height of the box, total number of pixels in the box. All these are the different features that you can extract. And for this particular instance, this is a feature vector, right? And the label is G, right? So this is how the data is looking like. So like that, we have 26 classes, A to Z, right? So therefore, we have 26 core functions. Each one of them gives the likelihood of a particular class. So for example, if you see the logistic regression, what is that corresponding function is giving? We have a multiple in logistic. If you see the logistic regression for multi-class classification problem, we are computing the score of the individual classes, and finally we are computing the probability of each and every class, isn't it? So similarly, here also we have 26 core functions. Each of them will give the likelihood of that particular class. Okay, so each of them assign a score for the corresponding class. For example, FA of X assigns a score for class A, B of X assigns a score for class B, and so on. Okay, and we use these scores to compute the probabilities. So probability that it is A is e power f of A by f of A of X, FA of X by the all the individual scores, e power the all the individual scores, sum over all the individual scores A to Z. Okay, similarly, we compute the probability for B, we compute the probability for C, and so on, probability for Z. And what is the predicted label? The class with the highest probability is the predicted label. Right? So very simple. It is like extension of logistic regression to multi-class classification problem. We are computing the probability for each and every class. Whichever class gets the higher probability, highest probability, we assign that class label as the predicted label. Right? So this is the model. Okay, so if you turn out this label yi into probability distribution, if you take the original probability distribution, if the label is z, it means what? According to the true probability distribution, the probability that y is z is 1 and rest of them it is 0. Right? Like this. The true probability distribution in the case of label G is this. For label G it is 1, for rest of them it is 0. Did you get it? So suppose if there is an instance x5 for which y5 is equivalent to g. So if I ask you the probability distribution for this particular instance, what is it? How the probabilities are distributed in A to Z scale. So A, B, C, so on G, Z, so on Z. Right. So we already know that it is G. So we are very much certain about this. So the probability of G is 1. So this is G, 1. And we are very sure that it is not A, it is not B, it is not C, and so on, it is not Z. So that is why for rest of them the probability is 0. So this is the true probability distribution according to the given label, right? So this is the true probability distribution, and we compute the predicted probability distribution using the predicted probability distribution function that we have described in the previous slide using this. So we compute the probabilities. These are the predicted probabilities. We know the true probability distribution and we are computing the predicted probability distribution using score functions FA to FZ. Right? So this is little tricky. That is why in one of the slides it is mentioned that the gradient boosting for classification is little difficult than gradient boosting for regression. So just pay attention. Right. So this is the true probability distribution and this is the predicted probability distribution. According to the score functions and the probabilities we are computing like this and we have got the predicted probability distribution as this. So if you plot them, this is the predicted probability distribution, right? And this is the true probability distribution. And what is our objective? What is our objective? We want to estimate the predicted probability distribution as closely as possible to the true probability distribution, isn't it? Suppose you given two probability distribution. One is true probability distribution, another one is predicted probability distribution. What would you do? You want to estimate this predicted probability distribution as closely as possible to the true probability distribution. Isn't it our objective? Yes or no? Yes. Cool. Yeah, yes. Right. So predicted probability distribution, it is based on the correct model. And we calculate the difference between the true probability distribution and the predicted probability distribution. So how do we compute the difference between the probability distributions? We use the concept of KL divergence to find out the difference between the true probability distribution and the predicted probability distribution. So what is this KL divergence? Let us see. So KL divergence is formally defined as dKL of P given Q is equivalent to sum over equal to 1 to n P of xi log P of xi by Q of xi, where Q of x is the approximated probability distribution and P of xi is the true probability distribution. Okay, and P of xi is the distribution of a particular instance xi. Right? Tentatively, this means that how much a given arbitrary distribution is away from the true probability distribution. Right? So we want to estimate how this Q of xi is different from P of xi. Q of xi is the predicted probability distribution and P of xi is the true probability distribution. So we want to estimate how different this Q of xi is from P of xi. So we use the concept of KL divergence. Yes, yes. Right. So we minimize the total loss. That means the KL divergence. So if you see the regression objective, what is the loss? We want to minimize the difference between the actual and the predicted values. But here we are expressing this actual and predicted in terms of the probability distributions. So therefore, we want to minimize the difference between the actual and the predicted probability distributions. And to compute the difference between the actual and predicted probability distributions, we use the concept of KL divergence. Means for each data point, we wish the predicted probability distribution to match with the true probability distribution as closely as possible. Okay, so that is the idea. So this is the true probability distribution. At round 0, assume that all the classes are equiprobable. It means each and every instance has got equal probability. Each and every, class label has got equal probability. Right? So over the number of iterations, as you can see that probability of G is increasing, right? So because your objective is to minimize the difference between the true probability distribution and predicted probability distribution. And the true probability distribution has got 1 at G and 0 at the other places. So in the process of minimizing this loss function through gradient descent algorithm, you can see that for G, probability is increasing and for rest of them, it is decreasing. So it is the results at the 100 round. So if you go for 200 rounds or 300 rounds, maybe it will be very much close to the true probability distribution. Right? So the goal is to minimize the total loss using the KL divergence. Loss is KL divergence. And for each data point, we wish to predict the probability distribution to match with the true probability distribution. And we achieve this goal by adjusting the models FA, FB, so on, FZ. So if you do the regression, gradient boosting for regression, we are adjusting one model, which is F equal to F plus H. But here we have got 26 models. 26 is the number of classes. So we have models equivalent to number of models equivalent to the number of class labels. Right? So we have to adjust how many models now? 1 or 26?
26.
26 models will have to adjust. Right. So this is our general procedure for the regression. Just to review, we're starting with the initial model F, calculating the negative gradient descent minus z of x, and fitting a regression model to the negative gradient descent and updating the model as f equal to f plus h. So this is what we have done in case of regression. So let's see for the classification. For the classification, we have 26 models instead of one model in case of regression. So the difference is here we have 26 models, whereas in case of regression, we have only one model. Right? So there we have a matrix of parameters to there we have a column of parameters to optimize. Here we have a matrix of parameters to optimize. Right? So we have FA of x1, FA of x2, so on, FA of xn, and FB of xn, FB of x2, so on, FB of xn, and so on, FZ of x1, FZ of x2, so on, FZ of xn. Whereas if you take regression, we only have f of x1, f of x2, so on, f of xn. So therefore, because we have multiple parameters to optimize, we need to compute multiple gradients, right? A matrix of gradients as in contrast to the column of gradients in case of regression problem. So we need to compute derivative of the loss function with respect to FA of x1, FA of x2, so on, FA of xn, and derivative of loss function with respect to FZ of x1, FZ of x2, so on, FZ of xn. Okay, so this is the algorithm. We start with initial models FA, FB, FC, so on, FZ, and we iterate until convergence. What are we doing? We are computing the negative gradients for each and every class. Minus z of x1, xi, minus z of zv of xi, so on, zz of xi. So where z of xi is derivative of loss function with respect to fa of xi. Right. So once we compute this gradient, we fit a regression tree. Regression tree is mentioned here, but it is actually classification model, some classification model, because we're trying to solve classification problem here. Right. So classification model to this negative gradient minus z of xi, minus zv of xi, so on, minus zz of xi. Once we get these models, HA, HB, so on, HZ, what are we doing? We are updating the models. FA equal to FA plus HA, FB equal to FA, and another mistake is here. This is FB. FB equal to FB plus HB, FZ equal to FZ plus SZ. Right. So alright, so this is what we do here. Any queries so far? Any doubt? If you don't understand something, please let me know.
Excuse me, sir. So class scores FA and FB, are they, is there any procedure? It varies with problem or
Sorry, FA, FB, FC, so on.
that these are the scores which we are assigned, which we have assigned to each class, sir. Is there any generic procedure common to all problems, or is it is domain specific or problem specific?
This is classification specific.
Okay, sir. Is there any formula, formula if it is binary or
This is generalized for multi-class.
okay, sir.
Because you can see this, no? This is for
Yes,
26 classes. It means it is a
26 classes.
multi-class class.
Yes, sir. Yes, sir. Thank you, sir.
Right. So if you see, this negative gradient is equivalent to the residual part, y of xi minus p of xi. All right. So you'll see the example, right? So at round 0, and these are the labels y. I'm not sure whether you could see this or not, but if you could not see, please zoom it. Please zoom it. Right. So these are the y labels. This is T, this is I, D, N, G. Okay. So if you see the true probability distribution for T, what should be the true probability distribution for T? Anyone?
0.
True probability distribution for T. 0 made up where it is 0, where it is 1. Yeah, Srinivas said T it is 1, and for rest of them it
Rather,
is
it is
yeah,
0.
yeah. So if you see this, YA is 0, sorry, YA is 0, YB is 0, YC is 0, so on till
T.
YT, where is it? Yeah, YS it is 0, but YT it is 1, this part. You can see that, right? YT is 1, rest of them it is 0. Okay, so only for YT, where my marker is present, that is 1. Rest of them it is 0. The next label is I. So what is the true probability distribution?
At YI it is 1 and for others
Rest
it is
of them
0.
it is 0. So YA it is 1. You can see that rest of them it is 0. Similarly for D, YD is 1. Rest of them it is 0. And G, for YG it is 1. For rest of them it is 0. So this is the true probability distribution table. These are the instance numbers. I equal to 1, 2, 3, 4, so on. Okay. And these are the initial scores. Initially, we are assigning a 0 score for each and every entry, right? FA is 0, FB is 0, so on, FZ is 0 for all the instances. So initial is a model is 0 score for all the instances. Now, once we have the scores, we can compute the probabilities, right? Using that formula, e power f of a by sum over I equal to 1 to n fi of xi, e power fa of xi, sorry, fc of xi. C is the class, isn't it? So sorry, if I made you confused, I'll just go to that part. Yeah, this one. So using this, you can compute the probabilities. Yes. Where is that example? Yeah. So we have computed the probabilities. As the scores are equals, we have got the probabilities also as equal. All the entries are 0.04 if you see. So what next? You have to compute the residual part, YA minus PA. So which is the negative gradient, right? YA minus PA is, we have computed, we have got the entries as minus 0.04 at every place. Correct? So we've got all these entries as minus 0.04. Okay. So using, now we have learned the rules using that function. These are the rules. H of x equal to 0.98, feature 10 of x less than. This is the regression model. not regression model, some decision tree like model we are fitting. This is HA of X, this is HB of X, this is HZ of X. Okay, so we are learning this model H and we are adding this model to this existing model. We are updating the model as this. FA equal to FA plus HA, FB equal to FB plus HB, FZ equal to FZ plus HZ. Okay, so we fit the model to this residual term and we get these models, and once we get the model, we are updating the existing model FA equal to FA plus HA. Right? We're just fitting this model to the negative gradient. Once we get this, what we are getting. Right? So now update this scores. Update this scores according to this new model. Right? So for this, these are the scores, individual scores at the individual entries, and according to the scores, we have computed the corresponding probabilities PA, PB, PC, so on, PZ for all the instances. And again compute this YA minus PA and again fit the model. Right? So this is the model at this level and we are adding this model to the existing model. We are updating the existing models FA to FZ. And again compute the score. Again compute the probabilities and compute this difference between the actual and the predicted. Okay, true probability distribution and the predicted probability distribution. Right? So, and again fit the model. So if you repeat this process at round 10, sorry, round 100, these are the values. So if you see the probabilities distribution, so this is the predicted probability distribution. This is of course true probability distribution. This will not change. So if you see the predicted probability distribution at round 100, so in this row, where it is maximum? For PT, isn't it? 0.79. For the other values, it is close to 0.1 or 0. So if you see, the predicted probability distribution is close to the true probability distribution after 100 iterations. Agree? Because if you see the probability PT, it is 0.79. Rest of the values, it is very low. Similarly, for I, if you see here, Pi is how much? 0.12. Rest of them it is less than that. G, if you see G, so PG is 0.42, and for rest of them it is less than that. N, if you see, what is PN? PN, MN, yeah, N here 0.59, and for rest of them it is less than that. Okay, so it means what? You're getting this predicted probability distribution close to the true probability distribution. Agree?
Sir,
Yeah.
here I have one doubt. For
Yes,
I, here you see for P it is 0.32 and PI it is 0.12, sir. So this
yeah, PG it
0.32
is
is more
0.32,
than,
PI 0.12. Yeah,
so it is more
yeah,
than,
more than that, yes. So
yeah.
if you repeat the process for more number of iterations, you may get closer to it. And even if you don't get some of the instances, there may be some error. Like even if we are doing regression or classification, some of the instances it makes some mistake, no. So it is something similar to that.
Okay, sir, thank you.
The possibility of misclassification or misprediction. Then you can consider that as a training error.
Okay, sir, thank you.
Yeah. So is that clear? Yes. Right. Good. So here we have not covered how to choose the proper learning rate. That row wala we are discussing now when we are updating the model. So that we have not covered. And the other possible loss functions we have not seen. If you want, you can refer to these papers and go through them. So these are the references. So that's all. If you have any query, I'll take. Otherwise we'll go to the demonstration part and we'll quickly go through the demonstration part and take 15-minute break, and then you continue with the next session. Any query? All right. So you can have gradient descent regression, gradient boosting regression, gradient boosting classifier. All these models are there, and various ensemble techniques are also there. So we are now talking about gradient descent regression in this demonstration. So I'm importing ensemble from sklearn, and I can directly import regression also, like sklearn regression. I'll show you that. Wait, this one. Gradient boosting regression. Okay, like this gradient boosting classifier is also there, right? So you can directly import this instead of importing the whole ensemble library. You can just from sklearn.ensemble you can import gradient boosting regression. All right. So these are the models, and the base model that I'm using is linear regression. So that is why I've imported linear model module here. But here also the same thing. You can directly import linear regression from sklearn, right? And this is the data set that we are generating here, like this. This is something like this, which is complex, where the regression model cannot fit to this perfectly, right? Isn't it? So we have to see that kind of data, right? So that is why we've generated data something like this. And we try to fit regression model, linear regression model to it and see how the model is looking like, right? So this is, we're calling linear regression model. You can see linear regression model we have got, and we fit that model to this data x and y, and we're just plotting that model. How is it looking like? You can see that we have plotted x and prediction, linear regression prediction, and color is red. So this is the model. So once I plot, this is how the model is looking like. So do you think it is fitting well to the data? Linear regression model, is it doing well? Do you think it is good fit to the data?
No, sir.
Not at all, right? So it's nowhere close to this, right? So let me plot the residual parts where this linear regression model is not doing well. So if I plot the residual parts, so this is the residual part. Okay, so there is a lot of residuals. I mean, there is a huge range for the residuals, right? So it means that this linear regression is not doing well on this. So let me take the gradient boosting algorithm. Right? So these are the parameters required by the gradient boosting technique. Number of estimators, how many number of estimators, it means how many number of rounds. Maximum depth, which is the depth of the regression tree. And learning rate is one, that is row that we are taking, and criterion based on which we want to minimize is mean square error. So if you want to change the criterion to some other loss function, there are some other options, you can choose them as well. Okay, so here we are taking mean square error as the criterion, right? So I'm calling this ensemble dot gradient boosting regression by passing these parameters. So these are the parameters that I've already defined here. So these are the parameters, number of estimators, max depth, learning rate, criterion. All these are the parameters which I've already defined. I'm just passing these parameters to this function. Okay, so once I pass these parameters, I've got the model, gradient boosting regression model. I'm just fitting the model to the data here, x and y I'm fitting, right? And I'm just plotting it with one estimator and single tree split, right? So I've taken only one estimator, no? It means only one iteration. And single tree split. Single tree split means very simple model, very basic model I'm taking, right? Because the complexity of the tree is only restricted to one node. So therefore it is very simple tree, right? So this is the model. Do you think it is better than the previous model? Yes or no? At least the bottom one, it is close to the actual value. A bit better than the previous model, yes. But do you think it is um, good fit to the data?
No.
No, not at all. Right. So let us try to, so these are the residual parts. So as compared to the previous one, it is doing a bit better as you have told, right? So now let me increase the number of estimator to 2. So I've just updated the number of estimator to 2. I am keeping the rest of the parameters as same. Okay, so rest of the parameters are same. I'm just changing this number of estimator to 2. So rest of the things are same. Only thing I'm changing is this number of estimators, n estimators, this one, right? So the rest of the things are same. I've just updated that to 2 estimators. Okay, again, I'm calling this gradient boosting regression with the updated parameters, fitting the model, and then plotting this curve. Okay, so this is the model. Isn't it better than the previous one? Little better, right? Little better, right? Number of, yeah. So let me increase the number of estimators. Let me try for the number of estimators for different values of number of estimators. So I've repeated this process for number of estimators in this. I've tried 5, I've tried 10 number of estimators, I've tried 20 number of estimators, I've also tried 50 number of estimators. Okay, then just plotting all of them as I have taken 4 parameters. I've taken a subplots of 2 by 2 size and figure size is 15 by 10. Okay. So if you see in each and every iteration, I get one of these and I'm just setting up that to parameters of number of estimator to n estimators. I'm just taking this n estimators from one of this and updating this in the parameters. So first time when the loop runs first time, I get 5 in this. When the second time it runs, I get 10, third time 20, fourth time 50 I will get. Every time I'm updating this parameter and estimators in the parameters and training a model with the updated parameters. So I'm calling the model with the updated parameters and fitting this to the data. Okay, and this is the code where should I plot that particular graph corresponding to 5, where should I plot, corresponding to 10, where should I plot, right? So the corresponding axis, I'm just defining, like I'm saying that 5 estimator should be here, 5 estimator, 10 estimator should be here, and 20 estimator to be here. Using some index calculations, I'm doing that. So if you see, for 5 estimators, it is better than the 2 estimators. If you take 10 estimators, it is better than 5 estimators. Remember, all of them base model is same, single tree split. Very simple model you are taking as the base model, but you're just increasing the number of estimators. With 5 estimators, we have got the first model. With the 10 estimators, we have got this model, and with 20 estimators, we have got this model, and with 50 estimators, we've got this model. Which model is better out of all this? 50 estimators, we have got the better model, isn't it? So with 50 estimators, we have got a better model, which is very close to the actual data, right? So you can see this, right? Single linear regression model couldn't fit it, but if you repeat the procedure for 50 number of times, it is compensating the shortcomings of the existing model and you are improving on it, right? So this is the effect of the number of iterations. If you number of estimators, if you increase the number of estimators, then your model performance is improving. So let us see whether increasing the complexity of the base model will have any effect on the model's performance. Okay. So here we have taken single tree split. It means very simple model we have taken. Let us increase the depth of the tree. So earlier we have taken depth as 1. Now you are increasing the depth to 2, depth to 3, depth to 5 and so on. Right. So we are fixing the number of estimators to 10. So this is fixed. Number of estimators is fixed. What are we changing? We are just changing the max depth of the tree. It means the complexity of the model we are increasing. So the complexity of the model, maximum depth is 1, maximum depth is 2, maximum depth is 3, maximum depth is 5. So we have tried different depths. So these are the parameters if you just want to look at it once. So these are the parameters. So in one case, we have fixed the maximum depth to 1 and changed the number of estimators and seen that number of estimators, by increasing the number of estimators, we have improved the performance. Now we are fixing the number of estimators, but changing the complexity of the underlying model. Complexity is increased. Okay, so let us see whether the model performance is improving or not with the complexity of the underlying model. Okay, so I'm changing the depth. So depth is 1, depth is 2, depth is 3, depth is 5. Right? So with depth 1, this is the model 10 estimators. With depth 2, this is the model same 10 estimators. And depth 3, this is the model, and depth 5, this is the model. So which is the better model? 5, right? So it's not only that number of increasing the number of estimators, by increasing the complexity of the underlying model also, it is actually improving the model's performance, right? Question from Brinda ma'am, isn't it overfitting to this data? Actually, there is a little overfitting, but in most of the cases, um, in case of this ensemble learning methods, actually overfitting is not that much in case of ensemble learning methods. It follows the true probability distribution. There may be a little overfit, I agree. Previously also this discussion came once. Yeah, but not, yeah. All right. Any other query? Any query?
Excuse me, sir.
Uh,
So max depth in the sense, complex is the degree of. Actually, I didn't get the concept of max
this is
depth.
assume that this is the regression tree, that underlying model that you're taking is the regression tree.
Okay, okay,
Regression tree, it means the decision tree or the regression tree. Decision tree where regression is the regression tree. Okay. So
okay.
we have, if you see the decision tree model, we are fixing the depth,
Yes, sir.
as a pre-pruning technique.
Yes,
So if you fix the depth to only 1, it means that you are only considering the root level model for
yes,
classification or regression problem.
yes.
Second level means it means complexity is little more. Third level means you are increasing the complexity. It's like
Okay.
that. Yeah.
So any model can be with this concept of boosting. Any model can be assumed, can be solved as with this by projecting it onto a decision tree with the help of boosting. A kind
Yeah,
of.
fine. Yeah, you can you can use it for regression, you can use it for classification. You
Yes.
can, yeah.
So even suppose if you want to perform boosting on SVM, even that can be used this way. My doubt is
It
that
can be used. It can be used.
yes, yes. Thank you, sir.
But there are some parameters that you need to change.
So depth will remain and extra parameters will also be added.
Some, yeah, some other parameters are there. You have to set those parameters.
Yes, yes. Thank you, sir.
Brinda ma'am, for some of the problems, I think I've already shared this link where you can get it from the scratch. If it is missing for some topics, you may please search. It is very easy to get. It is given in, this useful links for document. All right, if no queries, then take break of 15 minutes and come back by 6:30. All right, fine.
Sir,
Thank
will the
you.
video link that you have provided last for 1 month at least?
Sorry.
So the video link that you have provided will last for 1 month, means active.
Yes, yes. I mean, at least 1 month it will be available. After that, we are not sure about it.
Okay.
If the drive is, I mean, getting full, then we may delete this. I'm not saying it will be restricted to 1 month, but it will be available for at least 1 month. That is for
Okay.
sure. After one
Okay.
month, it may be available, may not be available.
Okay, sir. Thank you, sir.
Okay. Where sir, Srinivas sir? Only for Sandhya ma'am lectures you are saying? Srinivas sir? Oh, madam shared some link with you. So actually, in the folder, I am sharing these links. If you have not realized this video recording links, day-wise I am sharing. You can see this. So this is there in the folder that I have shared with you. So day-wise I am sharing. Day 1, day 2, day 3, so on till day 6 it is available, and today is day 7. Yeah. Alright. Thank you very much. So please come back by 6:30.
Good evening, Ananda. Can you hear me? Can you hear me? Yeah. My voice, is it clear? Or any disturbance? If
Yes,
no
sir, there is
disturbance,
some
okay.
disturbance.
Okay. Thank you. Okay. Myself, Dr. Balaprakash Rao, working as an assistant professor at NIT Warangal. So this session, I'm going to cover this reinforcement learning and its applications. And tomorrow I'm going to demonstrate this in Python. First, let me cover some of the basics of this reinforcement learning, because there are people from different branches of engineering and science. That's why let me cover the basics of reinforcement learning first. What is what, the terminology of reinforcement learning, and so on. When exactly we apply reinforcement learning, all this we'll cover now. So I hope you can see my screen, right? Okay, I think this is enough. Is it enough? The screen size, is it enough, or you want me to full screen? I think I already file view. No, full screen mode on. Okay, this is full screen mode. Okay. Okay, I hope you can hear me. You can see my screen. If not, please let me know. Okay. So this is the overview of the presentation. First, we'll see what exactly is the reinforcement learning. Where exactly this reinforcement learning falls under different fields of science and engineering. Then in machine learning, where exactly we study this reinforcement learning. And then we'll see some of the applications of reinforcement learning, that is section 1. Then we are going to introduce some of the basic terminologies in reinforcement learning, such as what is reward, what is environment, what is state, and some of the important entities like what is agent, what is environment, how they both interact with each other. These terminologies we'll see, that is section 2. So in section 3, one of the main component inside reinforcement learning is this agent. So we'll see the inner components of agent, reinforcement learning agent. So some of the important components of reinforcement learning agent, like what is policy, what is value function, what is model, all these things we'll see mathematically, and with examples also we'll see all these things. To clear doubts, we'll see with examples also. That is section 3. So in the end, we'll see there are different problems inside reinforcement learning, such as different people in different literature. You may come across problems like planning, reinforcement learning, how exactly they both are different. And then this model-based approaches and model-free approaches for reinforcement learning. Then what is exploration, what is exploitation, how they both are useful. and then we'll see what is control problem, what is estimation, how they both are different, and how they are related also. These things we'll see. That is section 4. So let us start our presentation with reinforcement learning. So if you see this Venn diagram, you can observe that the reinforcement learning, which was highlighted in blue, was at the center of all these circles. So what are these circles? These circles are different fields of science and engineering. Let us say this circle. Can you see my screen, right? My arrow, right? This one, mouse pointer. So this circle, it corresponds to computer science. So different fields of science and engineering includes computer science, neuroscience, psychology, economics, mathematics, engineering. All these are different fields of science and engineering. And if you observe even closely, what you can see is in computer science, there is a subfield of computer science called machine learning. Similarly, in mathematics, there is a subfield of this one called operations research. In economics, there is a subfield called game theory or utility theory. Different names are there. Bounded rationality. All these are same. Game theory, utility theory, and bounded rationality. So exactly, I am discussing about these subfields because from this Venn diagram, what we can conclude is there are these different fields of science and engineering, and there is a branch of each of these subfields, and which exactly deals with the same problem as that of reinforcement learning. That's why this reinforcement learning is at the intersection of all these branches of these fields of different fields of science and engineering. So in computer science, we study this reinforcement learning under the umbrella of machine learning. So in mathematics, we study it under the umbrella of operations research. That means the problems, the kind of problems that we deal with in operations research and the kind of problems that we deal with in reinforcement learning under the umbrella of machine learning, they both are almost similar. Similarly, core branches of engineering like mechanical, electronics, electrical people, they deal with some problem known as optimal control. So electrical people and mechanical people, chemical people, these people, they know this problem of optimal control. And what they deal with in optimal control is same as that of reinforcement learning. So same economics, game theory, it both all are same. So there is a subfield of all these fields which exactly deals with the same problem as that of reinforcement learning. Now the question is, what is reinforcement learning? What is reinforcement learning? So basically, reinforcement learning is a science of decision making. That means problems wherein we have to make a sequence of actions. Those places, this reinforcement learning is a better model to use this reinforcement learning. So we'll see more details about this reinforcement learning. So in computer science, we study it under the umbrella of machine learning. I hope the traditional machine learning techniques such as supervised and unsupervised techniques were covered. If not, it will be covered in the subsequent classes. I hope supervised learning was at least covered, right? Supervised learning was covered, right? Classification, regression, these techniques were covered. Yeah. Unsupervised, Prashant? Unsupervised, is it covered?
Only PCA covered, sir.
Okay, only PCA covered. Okay, no issue then. Okay, no issue. That means they have given a brief description of this unsupervised learning also. So now we'll see how exactly this reinforcement learning differs from supervised and unsupervised. So far by this time, you must have known basics of this supervised and unsupervised. What exactly is supervised learning? What exactly is this unsupervised learning? Now we'll see some of the differences between reinforcement learning and the other techniques like supervised learning and unsupervised learning. So the first and important difference is that there is no supervisor. Then you may say that in unsupervised learning also there is no supervisor. In supervised learning there is a supervisor, but unsupervised learning there is no supervisor. Then comes this one. In addition to this no supervisor, there is something you see. There is no supervisor, but there is some reward signal. There is a feedback signal. So for every action, the agent will get some reward. The reward is called feedback signal. Okay, we'll see this reward signal and feedback signal. And then the next important difference is that the feedback is not instantaneous. Feedback is delayed by many time steps. That means what? You take a decision now. After many time steps later, you may realize that your decision is not good. or your decision is good. So let me give an example. Let us say you have selected some action and you got a reward of +10. So at that point, you may think that your current action is good, but your second action resulted in, let us say, a reward of +2, and your third action resulted in a reward of +1, and your fourth action resulted in a reward of -100. So therefore, after three time steps later, you will realize that your decision is not good. Okay. So that's why I'm saying feedback is not instantaneous. It may be delayed by many time steps. And then the other important difference is that time matters in reinforcement learning. That means what? The data set in sequential, then the data set used in supervised and unsupervised learning, the training examples are independent of each other. So you take some training data set and you have to train on that particular data set. And the training examples in that data set are independent. There is no relation between the training samples. Okay, they are independent and identically distributed samples. So in supervised learning and unsupervised learning, the training data set, the data inside the training set is IID, independent and identically distributed. But whereas in supervised, in reinforcement learning, the data is not independent. The data is related. Why the data is related? Okay, let me write here now, I think. Okay. Now let me write here. Suppose, let us say you are somewhere, you are in some ground somewhere. Okay. You means not you. You have a ground and we have a robot. Okay. Now the robot has to reach the other end of the room. And this ground or room has some objects somewhere between, like this. Objects are there here and there in between. Okay. This side also objects are there. Some objects are there here and there. Okay. Now let us say the possible actions are moving left or moving right for this robot. Okay. Now let us say the action is moving left. So if the robot moves towards left, then the object it sees, let us say a camera was attached to this robot. Okay. Now when it moves left, the object it sees is completely different from moves right. When it moves right, that means what? Suppose here it can see some data. Now when it moves left, so that means what? The data it sees at time instance t+1 depends on the action. When it moves left, it will see a different data. When it moves right, when it sees different data. So the data is actually correlated. So that is a fourth important difference between reinforcement learning and supervised learning and unsupervised learning. So at this point, let me introduce what is this reinforcement learning. What are the different components inside reinforcement learning? Let me introduce. So basically, these are the two important components inside reinforcement learning. So this is called agent. This is called agent. So agent is the brain of the reinforcement learning. So the goal of the reinforcement learning is to design algorithms or programs that sits inside this agent. So you have to design programs that run inside the reinforcement learning agent. So what these agents are, what this program will do? This program running inside agent is responsible for picking actions at every point of time. As I said, reinforcement learning is a sequential decision making. That means the agent has to take sequence of actions. Okay. How those actions will be decided? These actions will be decided by using the programs running inside the agent. Okay, using these programs, this agent will pick the actions at every point of time. We'll see what are these programs, all these algorithms. So this is the first entity, agent. What is second entity? Second entity is environment. So what is environment? Environment is the demonstration of the problem to be solved. What is demonstration of the problem to be solved means? Suppose a robot moving inside a ground. Now what is the environment? Environment is your ground. Okay. Suppose reinforcement learning can be used for solving games also. We'll see the applications. Suppose you are using reinforcement learning agent for playing some game. Then in that case, what is the environment? Environment is a simulated environment inside computer. So that is software, right? So environment can be a real world environment or environment can be a simulated environment. So this is the other component, environment. What is the first component? Agent. Agent is responsible for picking actions using programs running inside this agent. So the goal of reinforcement learning is to design or create programs or algorithms that runs inside this agent. Using these programs, the agent will pick its actions. So now again we'll come back to this slide. So basically this agent picks some action, then environment will return some reward and it will return some observation. So this is how the reinforcement learning framework works. So there are two components, agent and environment. Agent picks some action, then environment gives some reward and it gives some observation. We'll see what is this reward, what is these actions, all these things. So let me go back now. Okay, so these are the differences. There is no supervisor. In supervised learning, there is a supervisor. In unsupervised learning, there is no supervisor. But in reinforcement learning, there is no supervisor, but there is a feedback signal. And then there is not IID data. Data samples are not independent. Data samples depends on the action. If data it sees is different, it moves right, then the data it sees is completely different. So at this point, let me introduce some of the examples of reinforcement learning. So by this time, you should have known what are the examples of reinforcement learning. So problems wherein the agent has to make a sequence of actions, they all comes under this reinforcement learning applications. Let us say the first application. So we have a drone or some helicopter. You want the helicopter to perform certain stunt. Stunt means what? You want the helicopter to follow some trajectory. Okay. Now, what are the actions here? At every point of time, we have this. The agent has to make a decision whether to move straight, move left, move right, and what angle it has to move. All these parameters it has to decide, right? So at every time step, it has to decide what to do, what action to take. So these are the actions, and the action is not a single action. If the agent takes a single action, we are not done. It has to take a sequence of actions. So this is the first application of reinforcement learning. Similarly, there are other applications like, let us see the second application. It is like we have to design a reinforcement learning agent that plays the game against humans. And this reinforcement learning must defeat the world champion of that game. Let us say the game is chess game or backgammon game. Okay, now we have to design a reinforcement learning agent that has to defeat the world champion of chess. Okay, let us say Viswanathan Anand, it has to defeat. So how it will defeat? Basically, the agent will play the game again and again, again and again, again and again. And after some time, it will figure out how to defeat the world champion. So we'll see all these things. That is called model-free approach. We'll see this one. And other examples like investment portfolio means, suppose you have some money, you wanted to invest in stock market, where you, so there is a program called trading agent. So this trading agent will tell you where to invest, what to invest, means how much to invest, and when to invest, and when to take back your money. All these things, all these decisions will be given to you by this trading agent. So here also, if you see, the actions are not a single action. The agent has to pick a sequence of actions. So similarly, controlling a power station. Controlling a power station means what? Suppose electrical people, they know. So suppose you have some power station and you wanted to control many parameters, like some torque, at what speed those wheels has to rotate, something like this. These parameters has to be decided by this reinforcement learning agent at every time. Let us say for every half an hour or 1 hour, this agent has to pick decisions like whether to increase the speed or decrease the speed. All these things has to be decided by this agent. And now, so these parameters has to be decided in such a way that the power generation has to be maximized, means the maximum throughput has to be achieved. So similarly, in previous case, investment portfolio, what is the goal? Goal is that we should get maximum profit. So the agent has to tell us where to invest in such a way that we should get maximum return on investment. So similarly, we have a robot which is at one end of the room. You want the robot to move towards the other end of the room in presence of obstacles. All these are examples of reinforcement learning. So if you see, what is the common thing behind all these applications? The common thing is the reinforcement learning has to make a sequence of actions, not a single action. It has to make a sequence of actions. Any questions so far? If you have any questions, please post in chat box or you can ask me. Any questions so far? Okay, if no questions, I'll continue. If you have any questions, you can interrupt me or you can post in chat box. I'll check from time to time the chat box. Okay, now we'll see the terminologies inside this reinforcement learning. So I have shown you one figure. There I have simply said we have agent, we have environment. Agent picks actions and then environment returns reward and observation. What is this reward? All these things now we'll see. So what is this reward? Basically, reward is like a feedback signal. So reward is a scalar value, something, some 20 plus 20 minus 20 plus 15.5, all this. It is a single value, that's all. Now, what is the use of this reward? So based on the reward, we can say how well the agent is doing at any time step. Let us say at time step t, the reward it has received, the agent has received a reward of RT. If the RT is plus 10, so based on that, we can say that, okay, if it is positive, then we can say that, okay, it was good, it was doing good. If it is a large positive number, then we can say that, okay, it was doing extremely good. If it is some negative number, then we can say that, okay, the agent is not doing, means the current action is not that much good, that we can say. Okay. So for every action, it will get some reward. Now, what is the goal of reinforcement learning? Goal of the reinforcement learning is to maximize the sum of rewards over the time. So that is called cumulative reward. Cumulative reward means what? Sum of rewards accumulated over time. So let me draw here otherwise. So let us say the robot was moving from one step at every time step, let us say time step t. It has taken this action of moving left and it has got a reward of plus 10. Okay. Now at this time step t plus 1, it has taken a decision of moving right and it has got a reward of plus 50. Let us say, assume that for simplicity, at every step, it has two actions, either moving left or moving right. Assume that this is left, this is right, this is left, this is right, for simplicity, although they are not proper left and proper right. So at every time step, here also, it can take either left or either right. Now if it takes left and it has got a reward of plus 30, like this. Suppose now here it has moved right and it has got a reward of minus 20 because the goal is here. Let us say goal is here. If it has moved in this direction, then it would have near to goal. Right now it has to move left. If it moves right again, it will get minus 30, let us say. If it moves left, then it will get plus 20 reward. Finally, when it reaches the target, let us say it will get some reward of plus 100. So what is the goal? So let us say, now let me tell you at this point so that it will be easy. Okay, now this is also right. Okay, left, right, left, right. So here it can go here up to here. Left, this is right. So from here, it can go left. From here, it can go, let us say left. This is, so let us say, now when it is moving left, it is getting a reward of, assume that there are no obstacles here for simplicity, I am explaining. So when it is moving left, let us say, so here it is negative. You can take it as negative. Let us say it is minus 50. So for every left move, you are getting a reward of plus 50. Not every time, okay? Because from here, if it is moving left, then it is moving away from goal. In this case, it will get negative reward, minus, so let us say minus 30, something like that. So now if you see this one, what is the best way to move? You have to move in such a way that this reward has to be maximized. So the total reward that you will get before reaching the goal, it should be maximum. That is the goal of reinforcement learning. So now you may ask, so earlier we have discussed some applications of reinforcement learning. So what is the goal of this controlling a power station? The goal is to, what is the goal? Goal is to achieve maximum power generation, maximum throughput. But now how we are defining the goal? Goal we are defining as maximize the cumulative reward, maximize the sum of reward. Now you may ask, how come you are relating the goal with this rewards, sum of rewards? So there is this hypothesis called reward hypothesis. Basically, it says that you take any reinforcement learning problem, and the goal of that reinforcement learning problem can be equivalently described as the maximization of cumulative reward. So now let us see the same. So I may not prove this hypothesis, but I will try to convince you with some examples. So what are the examples? Let us say, let us take this fly stunt maneuvers. So here, what is the goal? Goal is to follow some trajectory. If you are not following trajectory, then that is not our goal. You want the helicopter to follow the trajectory. So what we do in this case, when the helicopter is following the trajectory, we give some positive reward. Let us say plus 10. So like here, in this example, okay. So this is our trajectory. Let us say this is the from here and it is here. Let us say here up to here, this is the, okay. Let me draw with some other circle, some other color. This is the trajectory. It has to follow so that it is the shortest path, because I am assuming that there are no obstacles, right? Now, so what I'm doing, you see, what we are doing, we are giving some positive reward when it is following the trajectory. So in this example, so you leave about all these values, assume that these are not correct values. Now what we are doing is, as long as it is following the trajectory, so that means when it moves left here, we give some positive reward, let us say plus 10. When it moves left again, we give plus 10. At this point, when it moves right, you give some negative reward of minus 10. Here also, when it takes this, when it moves right, then you give a reward of minus 10, like this. Now if we give like this, what is our goal? And you see, you give a negative reward when it is deviating from the trajectory, or when it crashes. Now what happens? You see, what the agent will do. What is our goal? Our goal is to maximize the sum of rewards. So obviously the agent will follow this path only, this trajectory only, because the goal of the agent is to maximize the sum of rewards. So as long as it follows the trajectory, it will accumulate the reward. It will accumulate positive reward. When it deviates from this trajectory, it will get negative reward. So basically, the goal of actual goal of reaching this target can be equivalently described by maximizing the cumulative reward. So similarly, same thing works with other examples also. You can see, okay, I will share the slides. You can go through these things. So you can convince yourself that you take any reinforcement learning problem. The goal of that reinforcement learning problem can be equivalently described by using maximization of cumulative reward. Any questions so far? Rewards and how we are using this cumulative rewards for describing goal. Any questions so far?
No, sir.
So is it clear how we described the goal of the reinforcement learning as maximization of cumulative reward?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay, yeah. So for all these problems also, you can convince yourself that the goal is same as maximization of the sum of rewards. If you maximize, means if you get maximum reward, then it is same as your actual goal. So this is just a description. So earlier we have seen the examples of reinforcement learning problems, right? All these problems are from different fields of science and engineering. You see, this is, let us say, fly stunt maneuvers in a helicopter. Let us say this is robotics. What is this? This is some games related to games. This is what? This is financial. This is electrical. Okay, this is also robotics. This is also games. Okay. Now, if you see these problems are from different domains: games, finance, electrical, mechanical, robotics, all these things, right? But what is the common thing behind all these problems? Sequential decision making. So the agent has to make a sequence of actions. So the unifying framework behind all these problems is known as sequential decision making. So the common thing behind all these problems is that the agent has to pick a sequence of actions so as to maximize their cumulative reward. This is the common thing behind all these problems. Okay, now, so that is reward. So you should be very clear with reward, because in our consequent examples, I will use this reward, and you should say why we are using that kind of rewards. Okay. So now we'll see the other terminologies. So we'll see agent. So agent we have already seen. So agent is responsible for picking action. And then, so this brain is for agent, and this world symbol is for environment. Now, how this reinforcement learning works? Agent picks an action, environment gives some reward, and it gives some observation. What is the observation now? What is observation? So in our previous game, okay, robotics game, when it moves left, then the part of the environment, suppose a camera was attached, that is what we assumed, a camera was attached to the robot. Now when it moves left, then it will see a different set of objects, right? They may be obstacles, or they may be objects also. Let us say wall is there like this. So this is called observation. When it moves left, the observation is this one. This part of the environment it can see. Similarly, and when it moves right, it will get a different observation. Based on the action, it will get observation. Is it clear? The observation means. Is it clear with the terminologies? So basically, agent is a software program. Environment means it can be a real world environment, or it can be simulated environment. Agent is a software program. Agent is responsible for picking actions. When it picks action, environment gives observation, and it will give you some reward. And this cycle continues. After receiving some reward and observation, the agent will pick next action. It will get corresponding reward and observation, and this cycle repeats. So okay, this cycle repeats. How long it will repeat? We'll see how long it will repeat. So at this point, let me introduce some two important notions inside reinforcement learning, known as history and state. So first we'll see what is this history. So what is history? History is the sequence of actions, observations, and rewards. The sequence of actions, observations, rewards is called history. So what is the use of this history? The use of the history is, now by this time we should ask the question that how this agent picks this action, right? So I already said that there are some programs that are running inside this agent, and using these programs, agent will pick this action, right? Now, okay, programs requires some data, right? In order to decide which action to take, it needs some data. Program, it has to process something, then only it can take decision, right? Simply writing a for loop and printing something will not give you anything, right? The agent is responsible for picking action. What is the next action? That means it has to process some data, right? What it will process? So the agent will process this history. The sequence of actions, observations, rewards were there, right? Let us say this is the action, then I have received this observation and reward. Then I have taken this action, I got this reward and this observation. So this agent, by using history, what the agent will do? Agent will pick its next action. So that is the idea of history. What is the use of history? Agent uses the history to decide its next action. So then we can say that, okay, history is very good because agent is using history, agent is processing history, and it is picking its next action. Similarly, the environment will gives observation and reward, right? Again, environment also uses this history to return this observation and reward. So basically, agent uses history to decide its next action. Environment uses history to decide the reward corresponding to the action and observation corresponding to the action. Then now one may say that, okay, reward is very good because using reward, agent is picking its next action, environment is picking its next observation and next reward. So everything is good, but there is a problem. What is the problem? The problem is that this history is very big. Let us say the sequence of actions are very in a continuous manner at every second or every 10 seconds. Let us say every 5 seconds, the agent has to pick some action. And if you take examples like, I have not covered many examples, like let us say an autonomous car, okay, driving, autonomous car, okay, driving, autonomous car, autonomous driving vehicle. Now, if you see this problem, the agent, the driving agent here, the driving agent has to decide which angle to turn the steering, when to apply brake, when to apply what is that, something other for accelerator. All these decisions it has to take. Not only that, then first of all, a camera will be attached to the vehicle. It will see the road, right? Observations. Those are observations. So what is the observations here? In this case, what is the observations? In this example, autonomous driving, what are the
The
observations?
road,
Road. Yeah, images or video feed of the road. It will get, right. Then based on the observations, and then it has to decide how much to steer the what is the steering, and all these things it has to decide. Now, see in this problem, at every fraction of second, it has to decide, right? Actions has to be taken in a fraction of seconds. So in this case, if you see the history will be very long. Let us say you have an history of 1 hour. Okay. In this case, what is history here? Sequence of actions, observations, rewards. Let us say for every 1 second, assume that t is 1 second. For every 1 second, the agent has to pick action. Now, in 1 second, 1 hour means what? 1 hour means 1 minute means 60 second, and 1 hour means 60 into 60, 360. Okay, 3,600 observations, 3,600 actions, 3,600 rewards. In this case, if you see, the rewards are very simple because the reward is a scalar value. You have to just store 3,600 values. That's all, right? If it is 1 lakh, we'll store 1 lakh values. It doesn't matter because storage is very, okay, very cheap. So we can store 1 lakh values, let us say 1 lakh KB, not even KB. Let us say use 1 KB for everything. So it is what maximum? Not even 1 GB, 1 MB, 100 MB. This is right. This is 100 MB of data. That's all. This rewards. Similarly, actions. Let us say the possible actions are okay, moving, steering by some angle. Okay, let us say angle you are storing, and then accelerating. Okay, by how much to accelerate and when to apply brake, whether you are applying brake or not. All this information, let us say again 1 KB, 1 KB for all this information. So again 100 MB. Okay, this is okay. Everything is okay. But if you see observations in this example, the observations are either images or video, right? Basically, it has to process some video only, video feed only. So the video feed for 1 hour, is large. Definitely at least 200 MB, 300 MB, right? Or 500 MB maybe. What do you say, right? These are images and images are video feed. So now if you see the history for 1 hour itself is let us say 500 MB or 1 GB, nearly 1 GB. Although I have taken small values here, let us say 512 MB. We'll approximate it. Now, in order to take its next decision, in a fraction of a second, the agent has to process this much of data. Now, I have taken this simple scenario of history with only 1 hour. But if you see the real cars, Tesla cars and those cars, they used to train on lots and lots of hours of data, hundreds and thousands of hours of data. Now, if you wanted to process huge amount of data in a span of second, is it feasible? Is it feasible for online environment? This kind of environment, autonomous driving. So because history, the problem here is history is very big. If you wanted to process history and if you want to take your next action, it may not be feasible in real environments. So now what is the solution? Okay, history is good, but it is not useful. What is the solution? Solution is to use the other notion called state. What is the state? State is a function of history. State is a function of this history. So everything that is required to decide your next action will be encoded in state. So state is a compact representation of history. What is state? State is a compact representation of history. Okay. So now using state, so we'll see how exactly we encode state for some problems I will describe. You may at this point okay. At this point you may be confused. What is the state? How to represent state of different problems? We'll see with examples. So basically, state is a concise form of history. Means it is a function of history. Using this state, now the agent can decide its next action, and using the state, environment can decide what is the next observation and what is the reward for a given action. So in literature, generally they use 3 types of state: environment state, agent state, and something known as information state. What is this environment state? As just now we have described, environment has to decide what is the next observation and what is the next reward. So environment uses something known as environment state to decide its next observation and next reward. So here you see the numbers. These green things means these are the white things inside this green. So these are the numbers used by environment to decide its next observation and next reward. Similarly, agent uses agent state to decide its next action. Okay. Now the third representation of state is called something known as information state. So basically, when you are coming up with a state representation for some problem, generally we use this notion of state, information state, also known as Markov state. Basically, this is an information theoretic concept. Basically, what it says is, suppose you are in some state ST. Okay, you are in some state ST, and the probability of next state given the current state is same as probability of next state given all of the state information beginning from S1, beginning from the initial state, S1, S2, and so on. That means what? Let me tell you here. Let us say you take the helicopter example or something, helicopter, let us say. This is your current state, ST. Okay. Now, if you want to determine where exactly you will be after taking some action, ST plus 1, you want to determine what is ST plus 1. And your action, you have taken some action, left or right or something, you have picked your action. Now, if you know ST, if you can determine ST plus 1, probability that you will you live about probabilities. If you know state ST, current state, this is current state, and you have picked, the agent has picked some action, this is the next state. So based on current state, the state information alone, if we can decide what is the next state, this is one thing. The other thing is, in order to determine your next state, not only the current state, you have to know all this sequence of states, st minus 1. Let us say at time t minus 1, the helicopter was here. At time t, it was here. At time t plus t minus 2, it was here, let us say. At time, let us say t naught, at the initial time, t naught, the helicopter was here. Okay. Now, if you know all the state information from st1 to, that means what, from s1 to st, if you know all this information, then you can determine t plus 1. You can determine t plus 1. In this case, what? If you know st, you can determine where you will be at time t plus 1. So, if you can determine st plus 1 only based on st, then what is the use of storing all this information? Is it required? First of all, tell me. If you have all this information, S1 to ST, then you can determine ST plus 1. On the other hand, what I am telling is, if you simply know ST, then you can determine ST plus 1. Then is it required to store all this information, all this state? Not required, right? So this is known as information theoretic, information state. That means if you know also Markov state. Markov state means what? If you know current state, then we can determine the next state. So let me give an example here. What is what are different state? What is Markov state and what is non-Markov state? What is Markov state? Markov state means what? If you know current state, you should be able to determine the next state. What is non-Markov state? If you know current state, next state cannot be determined from the current state. Okay, let us say helicopter. Let us say you know the position. We are storing the state as position. Now, you know the position. Now, can someone tell me where the helicopter will be at time t plus 1? Let us say helicopter is moving left. The action is left. Helicopter is moving towards left. Okay, can anyone write in chat box or can anyone tell me? Position is the current state. Can you determine the next state? The position of the helicopter at time t plus 1? Yes or no, first of all? Can you determine position of the helicopter? Let us say this is position.
Yes, sir.
Yes, how to determine? Prashant?
From current state and
No, how? Okay, you know the current position. Let us say this is longitude and latitude. Okay, longitude, latitude. Now at position, means next position is longitude dash and latitude dash. How to determine longitude, this updated position from the current position, from current longitude and latitude? Is it possible? Basically, it is not possible. It's
Basically, it's not possible.
with position information alone.
yes,
Because you have to know what is the velocity of the helicopter, velocity or acceleration, something. I am very poor in physics. So it has to know, means we have to store, in addition to this position, what we have to store? We have to store what is the velocity of the helicopter. Let us say, then the angular velocity, in which direction it is moving. Okay. And then let us say wind speed, all these things. Let us say wind speed, you leave it. Now, if you know the position, current position, and we know that the action is left, it is moving in this direction. And if you know velocity and angle in which it is moving, then we can determine this position and then velocity. Velocity can be determined, right? Because yeah, velocity and angle, all these things can be determined. So this kind of state representation is called Markov state. From the state information alone, you can determine the next state. Whereas with position information alone, from the current state, you may not be able to determine the next state. For this, what you have to know? You have to know from beginning. You have to know from S0, S1. This is the initial state. So from here, You can say that from S1 to S2 at in 1 seconds. From here it moved to here S2. So using this, what we can determine? We can determine velocity. All these things we can determine if we know the sequence of states. So this kind of state representation, position information alone, is called non-Markov state, whereas this kind of state representation is called Markov state. So basically Markov state is useful because from current state you can determine the next state. Although I am simplifying things here, probabilities are there. For time being, don't think too much about probabilities. So any questions so far? Let me give this other example. This is a simple example. Now if you see, we have a rat. Let us say you take this first episode. So the rat has seen this bulb light on and off 2 times. Then it has pulled something. Okay, then bell sound came. When bell sound came, then what it got? It got shock. It got electrified. Okay. Now the second episode is that it had some bell sound. Then it saw this light on and off. Then it has pulled the lever 2 times. Then what it got is it got a bread. Now this is the information the rat has so far. Okay, now this is the third episode. It has pulled the lever. It has seen light on and off. It has pulled the lever. It has heard this bell sound. Now what it will get? How to determine what it will get? Based on state. Let us say if you store the state information as this thing, let us say the number of, okay, first you see what is the agent state, last 3 items in the sequence. If this is your state, last 3 items in the sequence, then what it will get? It will get shock. On the other hand, if you are storing state as number of lights, number of levers, number of bell sounds, then what it will get? It will get bread. On the other hand, if you are storing entire sequence as state, then it will not match with this or this. So that means the existing data is not sufficient to determine the output. So this is what we mean by state. So basically, so this is about agents and states. So far we have discussed. So then this environment we are talking about, real world environment or simulated environment, right? So basically, if you see here, agent state and environment state, this environment state may or may not be visible to agent. If the environment state is completely visible to agent, then those kind of environments are called fully observable environments. So this is fully observable environment. So then the question is, okay, we are talking everything theory. How to model this mathematically? So there is a mathematical tool to model this environment called Markov decision process. So fully observable environments can be mathematically modeled using this Markov decision process. Similarly, if this environment state, if it is not fully visible to agent, if it is partially visible to agent, then it is called partially observable environments. Don't worry too much about this fully observable and partially observable environments. So now we'll see what exactly are the working ideas inside this agent. So tomorrow we'll, when I demonstrate also, these concepts will be very much useful. So an agent, inside agent, actually we have to know about these 3 important components: policy, value function, and model. Okay, policy, value function, and model. So as I mentioned you earlier, this agent runs some programs, right? And based on the programs, okay, these programs will take as input the state or history. That is okay. Now, what is the output of these programs? Actions, right? So now we'll see how it is related to these components. So what is first one? Policy. What is this policy? So policy basically describes the behavior of the agent. Behavior of the agent means what? What is the action to be taken at a given state? Suppose if the agent is at some state, then what action it should take? Let us say here. Okay, leave it here. Let me give example, then it will be clear. Then the second idea is called value function. What is this value function? This value function describes what is the total reward the agent will receive from this state onwards. That is value function. So we'll see value function is basically goodness of state and goodness of action. Suppose you are in some state. Let us say, let me tell you now. You are in some state. Okay. The same for simplicity. Let me give this. This is the goal. This is the goal. And here is a robot. Let me keep it here like a straight line. This is the robot. Now, let us say it was in. If it takes all leftmost, it will reach. It will reach the goal. So for every left move, you get a reward of plus 50. Okay, plus 50 everywhere, plus 50, plus 50, plus 50. Means what? 1, 2, 3, 4, 5. Total reward is 250. Now, when you take a right step, you get a reward of minus 50. Okay. Now from here also in 5 steps it can go. Let us say. Okay, it can go here, 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 here. Let us say in 5 steps it can go. And every time it got some plus 40 reward because from here it is moving. Let us say plus 50, you can say. Now, robot at this point, it has to pick an action, whether to move left or move right. Now, if the robot picks this action, then where it will go? This state it will go. When it moves right, where it will go? This state it will go. Okay, right? Now, from here onwards, how much reward it will get? How much reward it will get? 200. And what is the immediate reward it got? 50. So when it moves left, it got a reward of 50. And from this state onwards, what is the reward it got? 200. Now, coming to this right action, what is the immediate reward it got? If it moves right, immediately it will get a reward of minus 50. From here onwards, how much reward it will get? Okay, let us say 1, 2, 3, 4. In four steps it can go. It is 200. Okay, now, so here you see, here the total reward is 250. Here the total reward is minus 150. So basically, now which action is good? Left action is good. So therefore, the value function will tell you what is the goodness of state, and there is something called Q value function. It will tell you goodness of action. Suppose you are here, this is the state. What is the best action? Whether to move left or move right. So it will be given by this value function. This is called value function. This is called action value function. Q value. We'll say Q value. So that is value. The third important idea is called model. What is this model? Basically, model is agent's view of environment. So model is not how the environment looks like. Model is what the agent thinks of environment. So agent in agent brain, it has a image that okay, this environment looks like this one. That is called model. So let me explain these things with the example also. Okay. First, let me explain policy. What is policy? I have already described. Policy describes agent behavior. Agent behavior means what? if so, here we can say that here we have two policies. This is one path, this is other path. So this is one policy, policy 1, this is policy 2. So policy will tell which action to take at every state. If you are here, move left. 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 Like this. From this, you can go this way also. This is other policy. This, let us say, this is policy P2. This way it comes, this way it will go, and then it will go this way. This is policy P2, this is policy P3, let us say. So basically policy is mapping from state to action. Then it is called deterministic policy. That means what? For every state, we have a fixed action. Suppose you see here, it is a deterministic policy. When you are here, you are taking some action with probability 1. There is no uncertainty. When you are in some state, you take some action with probability 1. That's all. That is called deterministic policy. What is stochastic policy? Stochastic policy, you will have probabilities. What are the probabilities? Suppose you are in some state, you have multiple possible actions, A1, A2. Here also you have actions, left or right. But here we will take the action with probability 1. But here what? Here it will tell, the policy will tell, you take action A1 with probability 0.5 or 0.6. You take action A2 with probability 0.4. These are called stochastic policies. Means probabilities are involved. So now let me tell you this value function. Value function is what? Goodness and badness of states and goodness and badness of actions. Goodness of states can be defined using this value function. Goodness of actions can be defined using something known as action value function. So basically, what exactly is this value? What exactly is this value? It is sum of rewards. So in example also I have shown you the same thing. In this example you see what is value? Value of the state? Value of the state is 250. Value of the state is 250. Why value of the state is 250? Because the total reward that you accumulate from the state onwards, maximum reward that you accumulate is 250. From the state, what is the value? 200. From the state, 150. From the state, 100. Like this. From the state, 50. This is the value. So that's why if you see here, RT plus RT plus 1 plus RT plus 2 and so on. So it is like sum of rewards accumulated over time. Now here if you see, it is an infinite. It was moving. It was going on and on. Why it is still going? When it will end? This is the question I asked. When it will end? It will end when it reaches goal. When it reaches goal, then it will end. This sum of rewards, that's all. The sum will end there. So now we'll see what is model. So model is basically what? Agent's view of environment. Agents thinks that environment looks like this. This is not how an actual environment looks, but this is what the agent thinks. So there are two things in model. First one is called transition model. The second one is called reward model. The transition model will tell you if you are in some state, if you pick some action, what is the probability that you will end up in some state ST plus 1. Now you may ask, why the probabilities are coming? Why the probabilities are coming? So you are in some state, your action is left. Then I am telling that with probability 0.99, let us say, you will end up in this state, ST plus 1. Now you may ask, why with probability 0.99? Why not with probability 1? Because the action is left. After all, the action is left. Then the robot should go here with probability 1. Why with 0.99 probability it was going here, and with 0.01 probability it is going somewhere else? This is due to the noise in the environment. The noise may be like due to wind speed, means the air was coming in this direction, let us say. High speed wind is coming in this direction. Then the robot may end up here rather than ending up here. If you want more Easier example, let me give this example. This is one example, wind speed. So this is called the noise in the environment. Let me give more better example. Let us say you are at your office. Okay, you are at your office. Now it was 5 o'clock in the evening and you have decided to leave your office. Okay. So when you decided to leave, generally you come to your parking place. Okay. Now you will take your bike from here and you will go home. So you have decided. That's why you came to parking lot. You have decided to leave. So your action is to leave, not stay. Your action is to leave. If you want to stay, you will stay in the office only. Okay. Now, before what? So you reached your parking place, then rain came. Rain came. Assume that there is no rain suit with you. Now what will you do? Will you leave? If you have some urgent work, you may leave, even though it is raining. But mostly you will stay. So you will stay in the office, right? Although your action is to leave, you are not reaching home. Your next stage is not home. Your next state can be office also with some negligible probability. Not negligible, 0.001, let us say. This much probability you will stay in the office only, right? That's why these things are coming. Which one? Yeah, this one. This transition model probabilities are coming. So you are in some state. Your action is to move left or move right. So let us say move left. Then what is the probability there? What is the probability with which you will end up in this state, st plus 1? So let us say here, with 0.99 probability, you will end up in this state. With 0.01 probability, you will end up in st plus 1 dash. Is it clear? That is transition model. And then reward model. When it is in some state and then when it picks some action, what is the reward it will get? So this agent has some view of these models, transition models and reward models. Now let me explain all this math with a simple example, then it will be clear what is policy, what is value function, and what is model. So let us see this example. You take this example. If you see the example, the problem description goes like this. You have some robot here. You want the robot to reach the goal. Okay, you want the robot to reach the goal in shortest path, in minimum number of steps. You can say in minimum number of steps, right? Now, how the agent will reach the goal in minimum number of steps? How to model this problem now? Tell me. So, what are the actions? So far, we have seen actions. In this problem, what are the actions? Actions are moving up, moving left, moving right, moving down. These are the 4 possible actions, right? Now, what kind of rewards we'll use now? Tell me. You wanted to reach the goal in minimum number of steps. Should I use some plus 10? Is it okay? Can I use a reward of plus 10 for every time step? Yeah, okay, Prashant. So, okay. Yeah, Sahara. AK Sahara, sir. Okay. Now, suppose if you use plus 10 reward for every time step, then earlier we discussed the goal of the reinforcement learning problem can be equivalently described as maximization of cumulative reward. Now, you have taken a reward of plus 10 for every time step. Then what the agent will do? When it will get maximum reward? Can someone tell me when it will get maximum reward? It will come down. It will come down, and then it will come down, and then it will repeat here itself. It will not go to the goal because for every time step it is getting a reward of plus 10, right? Every step it is getting a reward, positive reward, plus 10.
Yes, sir.
So if it is repeating here itself, then what is there? Let us say it came here like this. You see my hand symbol. Then it moves left, then it moves right, moves left, moves right, moves left, moves right. Like this, it will repeat here itself. For every time step, it will get a reward of plus 10. So it is maximizing the reward. Yeah, reward should be based on, yeah, next some comment came, reward should be based on direction. But how you will give reward based on direction? The agent doesn't know where the goal is. You see, here the problem is the agent doesn't know about environment. It doesn't know where the goal is. The goal may be here, the goal may be here. This may be the goal. Or
Yes,
this may be the goal, or this may be the goal. You see,
Yes, sir.
it doesn't know which direction to move.
Okay.
Now, for this problem, what kind of rewards do you suggest? Plus 10 did not work. Do you think
Yes.
plus 1 will work? Plus 1 will work? Same problem.
Same problem.
Yeah, so what is our goal? You see, the goal is to reach the, goal is to reach the target in minimum number of steps. So therefore, for these kind of problems, we can use negative reward. You see, for every time step, you use a minus 10 reward or minus 1 reward. What happens when you use minus 1 reward? What happens when you use minus 1 reward? When you come down like this, let us say, now you see from here, what is the shortest path from start to goal? First of all, tell me, what is the shortest path? Shortest path is this one. Can you see?
Left. Yes, sir.
This one. This is the shortest path. Can I write here? Somewhere here. It was not here. Okay. So this is the shortest path. Now, for these kind of problems, I'm saying that I will use minus 1 reward. For every step, I will use a reward of minus 1. That's what it was described here. Minus 1 for every time step. Location is, state is agent location. Now you see here, the arrows here describes the policy. So what is policy? Let me go here, definition of policy. Policy is, it defines the agent behavior. It should tell what is the action corresponding to each state. Is it not? Now, when you come here, you see the arrow represents the action. When you are in this state, you move right. When you are in this state, you move up. When you are in this state, move right. Like this it was telling, right? When you are in this state, you move up. When you are in this state, move up. When you are in this state, move left, like this. Now, what is value function? What is value function? It is goodness of state, or you can say it is the maximum, the reward, total reward that it will accumulate. Now, if you see the numbers here represents value functions, I am telling. So what is this minus 15 will tell you now? What is minus 15 here?
The expected reward.
Yeah, the reward, it has, yeah, expected reward. Probabilities we are not talking. There, we can say this is the reward. So now, yeah, that is reward only. But what exactly it signifies physically? Here, what exactly this minus 15 signifies in this problem? If you see here in this direction, the numbers are decreasing. That means what? This minus 15 signifies that from this step, it is 15 steps away from the goal. From here, how many steps away from the goal? 16 steps. Let us say from here, how many steps it is away from the goal? 22 steps. From here, it is 24 steps away from the goal. Now, if you know value function, can you determine policy? You are here.
Sir. Yes.
What is the action? Only one action. Okay, you move right. That is okay. Okay, so we got this right arrow. That is okay. Now, when you are here, minus 15, you have two possible actions, move up or move down. When you move down, how many steps you are away from goal? 16 steps away
60.
from goal. When you move up, how many steps away from the goal? 14 steps away from the goal. So which action you will take? Which action the agent will pick? Up. Okay, that is the policy you see here. So this is the policy. Now suppose you are here. You have two actions, move right or move up. Basically, obviously it will pick this action of moving up. Okay, this way, so these values indicates how many steps it is away from the goal. Basically, value function signifies the total expected cumulative reward, means the expected cumulative reward it will get for the time from this state onwards. Okay, from this state onwards, it will get a reward of minus 15. Now we'll say this one, model. What is this model? Let us say the agent has followed this path to reach the goal. First time it has reached the goal using this path. Okay, it don't know these things. Okay, now what do you think the model of the agent will be? Model. So the agent has not explored the lower side of the environment, right? So the agent doesn't know this part of the environment. Agent only thinks that environment looks only like this, but this is how the environment looks. No, environment looks like this, you see. So as we already discussed, in model there are two things. What are the two things? First one is transition model, second one is reward model. So reward model will tell you, so since it has explored this path, it knows that if it takes this action, it will get a reward of -1. So here the number signifies the rewards. Now what is the transition? Suppose when it is here, it knows that it can move up or it can move down. So therefore these cells signifies transition model. From here you can move up or move down. So far any questions? Model, policy, value function? If you have any questions, please let me know. Yeah.
Yes, can we just know how the value function is computed based on the formula given for this example?
For this example.
Yes.
Based on the
It
formula.
seems
Yeah.
intuitive. It seems intuitive, but an example calculation makes it more clear.
Yeah. Tomorrow we'll demonstrate also. Okay. Let me.
So, because there is a gamma variable.
Yeah. Okay. Gamma I have skipped. Let me tell you gamma. Gamma I have skipped. Let me give some idea about the gamma also. So gamma here is called discount factor. So basically this discount factor signifies how much value you are giving for future rewards. Okay, so if you see these rewards, this is a value of some state S, right? Value of some state S. That means you are here and you are calculating value of S. But how you are calculating value of S? Suppose you have taken some action A, something, and you got some reward RT. From here you have taken some action, you got a reward of RT plus 1, and you are and so on like this, and so on. Okay. Now, if you simply take sum of rewards, we can take, right? What is the problem if we simply take sum of rewards?
There is a problem of cancellation.
Problem of not cancellation. This is it results in infinite loop.
Okay.
Right? It will go. There are other problems also. Let me tell you with this infinite loop first. Let us say some employee is getting some let us say 10 lakh rupees per month or 5 lakh rupees per some month. Okay, not month, yearly. This is per year. Monthly, who will get 10 lakh? Okay. Okay, 10 lakhs rupees per year. Is a normal employee is getting 10 lakh rupees per year. Now, for I am taking a simple assumption first to give a idea of this discount factor. Let us say he is immortal and the salary will not increase. Every year he will get 10 lakhs only. Now he wanted to calculate. How much money he will earn throughout his lifetime. So what is the formula? It is simply 10 plus 10 plus 10 plus 10 plus, it will go on, right?
Yes, sir.
So the first idea comes here. It results in infinite loop. It is difficult to compute the value. Now I wanted to calculate value in 2021. Means the total salary I will get from this time onwards, from 2021 onwards till end, till there is no end. It will go on. And the other reason for introducing this discount factor is generally people give more preference to immediate rewards over future rewards. So it is like this one. Let us say, suppose you have 1 lakh rupees with you. Okay, now, and you have 1 lakh rupees with you next year. So the best example is, let us say you wanted to buy gold for 1 lakh rupees. Okay. Then let
Okay,
us
sir.
say based on the current cost, you may get some 20 grams gold. So generally this gold price, it increases, let us say from year to year, assume that. Now in the next year, do you get the same gold? No, let us say you have for 1 lakh rupees, you got only 18 grams or some, let us say 10 grams only. It is easy for calculation. Easy for calculation. So that means what? 1 lakh. So right now, what is the cost of 10 grams?
And
50,000 only. So you have given your friend some money for loan, 1 lakh rupees. Now he has given these two options. I will give now, or I will give you 1 year later.
Yes, sir.
Now, if you get this 1 lakh after 1 year, you will get only 10 grams. But if you get this 1 lakh now, you will get 20 grams. That means what? What is the value of 1 lakh rupees? Next year's 1 lakh rupees. Now,
It's
50,000.
Yes,
So
sir.
this is called discount factor. So the gamma is 0.5.
Okay.
Gamma we take as 0.5. That means what is the present value of future reward? In future, I am getting this reward. Reward means my money only, but I am
Yes.
using this term reward, let us say.
Okay.
So in future, I am getting this reward.
Yeah.
But what is the value of this future reward now?
Yeah.
50,000 only. So you prefer immediate reward only over delayed reward. This is called delayed reward. Reward after 1 year.
Yes,
So
sir.
this is a common tendency of humans to prefer immediate reward over delayed rewards. This is the other reason for using this discount factor. So that's why what we do is we discount these delayed rewards. So in future reward, what we do is we calculate it as less reward. So it is like depreciation, you can say, not depreciation. What does inflation? Inflation,
Yes.
right? So
Yes,
if you
sir.
go to internet and if you see what is the value of 1 crore rupees after 20 years.
Yeah. It may be around 10
Yeah,
lakhs.
it may be around 20 lakhs or 10 lakhs. So what
Yes.
is this? So here the discount factor is 0.2 after 20
Yes.
years.
Yes,
So
sir.
this is the idea of discount factor. So
Yes.
in 20 years later, you are getting 1 crore. But after 20 years, what you will get for 1 lakh? Means 1 crore, you will get 20 lakhs rupees worth
Yes.
current value. So that's all. So this is the idea of discount factor. That's why generally we multiply future. These are the future rewards. In
Yes, sir.
calculating the reward, the cumulative reward at state S itself. But
Yes.
these rewards you will get in future.
Yes, sir.
That's why we are multiplying these with this gamma discount factor. This is the other reason, and there are many other reasons also due to uncertainty in the future.
Yes, sir.
And uncertainty in the future, like this one, the gold may increase, the uncertainty. The gold may decrease also, that is different.
Yes.
There is an uncertainty in the future also. That's why we use this discount factor.
Yes, sir. So gamma range is only between 0 to 1, sir.
0 to 1, that's all. Gamma 0 means what? If the gamma is 0 means what? If you see here, gamma 0 means what? All these terms were nullified. That means what?
Nullified.
There is no value for delayed reward. That means you are least interested in delayed reward. If someone
Yes.
says now or later, you will obviously say now only. I don't want later. Okay.
Yes, sir.
Gamma equals to 1 means what? Doesn't matter. You are giving same value.
Yes, sir.
Now for 1 year, you are least interested in money, then you can say that, okay, you give whenever you have. That's
Yeah.
all. Delayed reward. You are not giving any value to delay. Means no, you are giving same value to present reward and delayed rewards.
Yes, sir.
So with gamma ranges between 0 and 1. That's all.
Yes. Yes, sir. Thank you, sir.
Okay, so this is policy. These arrows represents policy. Policy will tell you what is the action to be taken at every state. This is value. Value will tell you expected cumulative reward.
Yes, sir.
And then this is model. Yeah, this we discussed. So now let me summarize everything. So reinforcement learning agents can be categorized into value-based RL agents or policy-based RL agents. Value-based RL agents only uses policy. They will not store any value function. They will only use a policy. That's all. No, yeah, the value-based means they use only value, no policy. But if you have value function, you can determine policy. Just now I have described here. If you have value function, let us say these values, then based on this, you can determine the action, right? So if you have value function, policy is implicit. Whereas policy-based RL agent means it uses policy. It doesn't use any value function. Whereas this actor predict is hybrid RL agent. That means it uses both value function and policy. Similarly, the RL agents can be categorized into model-based RL agent and model-free RL agent. So model-based RL agent or model-free RL agent can be a policy-based or value-based or combination of policy and value-based. What is this model-based and model-free RL agent? Now let me describe at this point. We have to give some idea of this model-free and model-based agent. So what is model-free agent and what is model-based agent? So yeah, this is total together: value-based, policy-based, model-based, model-free approach. All this. Now, what is model-free approach? Model-based approach. So model-free approach and model-based approach means, let us say, you have visited a new city. Let us say I have never visited Hyderabad and I visited Hyderabad, Secunderabad. Okay. Now you don't know anything about Secunderabad, but you have a Google map with you. You have a phone with this Google Maps capability. Okay. Phone with Google Maps capability. On the other hand, you take the other situation. You have a phone. It is only for dialing numbers. That's all. Phone with no GPS. Phone with no GPS and Google Maps capability. Okay. Now you wanted to, okay, you have taken some room somewhere. You are new to this city. You have your room. This is your room. Now you wanted to go from your room to your office. Okay. Now you have asked 3-4 people, what is the way from your room to your office? They will tell different ways. Okay, they will tell that, okay, this is one way. So you asked some stranger how to go from this location to my office. He has told, okay, this way you can go, this way you can go, this way you can go, different ways he has told. Now these are the possible actions. You can pick this action first, or you can go in this direction, or go in this direction, or go in this direction. These are the 4 actions now we have. Okay. So this is called model free approach. Then what you will do, you randomly pick some action. Out of these 4 paths, you pick some path randomly. Okay. You pick some action randomly. So you followed this path, let us say on first day. You have reached office. Now on second day, you have picked next path, this path. You have reached office. Then you have realized that the second path is better than first path. Okay. So here you see, you are randomly picking actions. This is called model free approach. You don't know anything about this environment, this Secunderabad city. You have randomly picked a path and you followed that path, and so let us say these are straight roads. Okay, these are straight paths. If you take this direction. This is that's all. If you follow that road, you will go to your office. So this is called model free approach. You don't have any information about environment. Here, what is the environment? Environment is your Secunderabad city. You don't know anything about any information about this environment city. Randomly, you have picked this action, action of moving to your office. On the other hand, you have phone with GPS capability. Then what you will do? You will search for location from your room to your office. Then it will show different directions. Then what you will do? It will give the best way to reach your office. Then you will reach the office using this best way. So here you see, you have the idea of environment, not directly, but this in terms of Google Map. The environment information is available in Google Map, and Google Map is giving you this information, right? So these are called model-based approach. Model is available to you. Here the model is Google Map, let's say. These are model-based approaches. If the model is available to you, then it is called model-based approach. If the model is not available to you, then they are called model-free approach. In model-free approaches, generally we start with some random actions. Okay, now let me introduce those problems. Okay. Now, generally in the sequential decision making, there are two problems. One is planning, the other one is reinforcement learning. So the model-based approach is known as planning, and the model-free approach is known as reinforcement learning. So in model-based environment, first we'll see model in reinforcement learning environment. What it will do, the agent interacts with the environment. Interacting means what? It will randomly pick some action. It will observe how much reward it will get. What is the next observation it has received? All these things it will observe. And then based on these observations and experience, it will improve its knowledge, and it will improve its policy. Okay, it will improve its decision making capability. That is reinforcement learning. What is planning? Planning, it will not interact with environment. You see, it has not randomly picked some action. You have sitting in a position, you have opened your Google Map and you have searched for paths from your room to your office. And you have computed this, your Google Map has computed the best path from room to office, and you have followed that path. So similarly in planning, environment is known to you. Agent, what it will do? It will not interact with the environment. It will do some computations. That means what? It will solve some mathematical equations using the available model. Then it will come up with the policy, and it will simply follow the policy. That is the difference between planning and reinforcement learning. Any questions here? Planning and reinforcement learning? Or any other ideas? Any questions so far? Okay, if no, let me introduce here. Now you will discuss this model free approach. So let us say first day you have visited using this first path, second day you have visited using the second path, and you have realized that second path is better than first path. On third day, will you go using the third path, or will you go using the second path, which is best so far? So here comes the problem of exploration versus exploitation. Exploration versus exploitation. What is exploration? Exploration means what? You pick a random path again. You have not fully this one explored, right? So you again pick this third one randomly, right? This is exploration. Exploitation means what? This is the information so far I have, and I know that second is better than first one. So this is the best path so far. So I will simply follow this path. So this is called exploitation. Exploitation means what? Using the existing knowledge and pick the best action based on the existing knowledge. That is exploitation. Exploration means what? Exploration means what? Visiting, exploring unexplored paths. Visiting unexplored paths. This is exploration. So in reinforcement learning, you have to always maintain a trade-off between exploration and exploitation. If you are always what? If you are always exploring, then what? Because exploring takes some time, because it is new to you, then it will take some time to reach your office, always. On the other hand, if you always exploit, then you may not explore, then you may not visit the unexplored paths. Let us say out of these 4 paths, this is the shortest path. If you are always exploiting based on the existing knowledge, then you will always follow the second path only. You may not get the shortest path. So therefore, we have to maintain a balance between exploration and exploitation. So generally, the reinforcement learning strategies, they use something known as epsilon greedy strategies. So with probability epsilon, they will take a random action, and with probability 1 minus epsilon, they will use the existing knowledge and pick the best action. And then I will close the session with these 2 things, prediction and control. I will introduce these 2 problems. What is prediction and what is control? What is prediction? If someone gives you policy, then you should evaluate the policy. That is called prediction. That means what? If you follow that policy means what? It will tell you what is the action to be taken at every state. So if someone gives you policy, what is the value of, what is the reward you will get by following this policy? That you have to evaluate. That is called prediction problem. What is control problem? Control problem means no one will give you policy. You have to find the best policy. Best policy means what? Policy that results in maximum reward, maximum expected cumulative reward. So this is an example of prediction problem. So here, let us say the policy is uniform random policy. Uniform random policy means what? Here the actions are up, left, right, down. You have to pick an action with probability 1/4. That is uniform. And random means what? Pick one of the action randomly based on some coin toss. You toss 2 coins. If the result is toss tail, you take up, tail head left, head tail right, head down, like this you take. So this is called uniform random policy. Is it clear? Uniform random policy. For this policy, you have to find value function. So this is called control problem. Here no one will tell you what is the policy. You have to find the best policy. Best policy means what? What is the best action at every state? If you are in some grid, what is the best action to take? That has to be determined. How to determine these 2 things? So tomorrow I will introduce this prediction. If someone gives you policy, how to find this value function, and then how to come up with this optimal policy. These things I will discuss tomorrow, and I will demonstrate. Any questions? Any questions? Any questions?
No, sir. Understood.
Why the strength is very less? 24. I don't know. Is it the effect of Sunday or every day like this? Okay, if no questions, then I will close the session. It is already 8 and Sunday.